Hi, I'm Professor Goins and welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in pretty much any college mathematics course, please consider subscribing and then checking out our playlists, watching our videos, and then once you watch them, like them, comment, share them with your friends. Any of those free interactions are greatly appreciated because it does help us to grow. Let's go ahead and get into the current video. I want to take a look at the closure of a set. Again, the closure of a set in sort of a general topological space. Let me start with the definition. For a set X, or I'm sorry, let's say for a set A in a topological space X tau, so in other words, A is a subset of X, again within this topological space. The closure of A is given by the intersection of all closed sets containing, A. Right? Now, the first thing we should probably check is to make sure that that's actually a closed set. It'd be fairly strange to call a set a closure if it wasn't actually closed. By the way, the notation is I'll put A with a bar on top. So A with a bar on top means the closure of the set A. Well, let's go ahead and take a look at the intersection of an arbitrary set of closed sets. If I take the intersection, let's say where A is contained in C and C is closed of the set C, okay? This is what the closure would be. It would be the intersection of all closed sets that contain C. Well, how do I check to see if this is actually a closed set? Well, remember that the relationship between open and closed sets is that they're complements. So if a set U is open, then its complement is closed. Conversely, if a set is closed, then its complement is open. Let's go ahead then and take a look at the complement of this particular set. Well, the intersection of a complement is going to be the union of the complements, where, of course, A is contained in C, and C is closed. If C is closed, then C complement is open, and this is an arbitrary union of open sets, which, of course, is an element of the topology. In other words, it's open. Therefore, the original intersection must be a closed set, and therefore the closure is, in fact, a closed set, which is what we would hope that it would be. Let's take a look at a specific example of finding a closure. All right, well, first example that I want to take a look at is let's look at the interval from 0 to 1, where 0 is included and 1 is not. And this is in the real line with the usual topology. Now, if I take the closure of this, we would certainly hope that the closure of this interval would be the closed interval between 0 to 1. So basically, I would just take this and add the 0.1 to it. And in fact, that is the case, where if I take the closure of this, I do get 0, 1. Okay? I'm not going to prove it. I'm just going to state a couple of results here. If I take the closure of that, I get the closed interval from 0 to 1. Similarly, if I take the rational numbers and I take the closure, Well, rational numbers are dense in the real line, and if I take the closure of those, I do in fact get the entire real line. Again, in the usual topology on the real numbers. Now let's look at an example of a topological space that is just, for practical or for discussion purposes. Let's say I've got X is the set consisting of, let's say, 1, 2, 3, 4, 5, 6, and 7. In other words, the topological space, the underlying set, consists of just the elements 1 through 7, and the topology on that, let's say, consists of the empty set and X, along with the singleton 1, the singleton 3. Of course, that's contained under, closed under union, so it has to have the set 1, 3. Let's say I've also got the set 6, 7. And then since it's closed under unions, it would also have to have 1, 6, 7, along with 3, 6, 7, and 1, 3, 6, 7. And then let's close it. So that right there would be a topology on that set. And let's say I want to look at the subset of X, A, which is given by 2, 4, 6. So what is the closure of 2, 4, 6 in the set 1, 2, 3, 4, 5, 6, 7, given this topology on that set? If I go back up to this example here on the real line, again, we have so much practical practical experience with using the real line, even when we didn't really understand topology or what the usual topology was. If I said, if I was going to close this, 0 to 1 seems like the most likely answer. And if I was to close the rationals, the real line, this seems like the most likely answer. Seems reasonable, right? But for this one here, if I close 2, 4, 6, what is that going to give me? Well, let me go ahead and clean up this side of the whiteboard, and I will show you how to actually construct that. One thing that I like about examples like this, let me just kind of make this comment off to the side here, is for one, it's not intuitive like it was up here with the real line, but it's small enough that we can actually construct the, say, closure or interior or boundary or whatever the case may be of these sets. So we can actually we have a finite list of sets, and not only is it finite, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 elements of the topology, 9 sets to work with. Whereas up here, if I say take the intersection of every possible closed set that contains 0 to 1, well, of course, there's uncountably many, but with this example, I'm actually able to list them and then work with them. So it's very constructive and allows me to really get an understanding of the definition. Well, let's go ahead then and take a look at the closed sets. In fact, I'm going to list all of them. I think it's kind of instructive to do that anyway. This right here is your topology. In other words, all of your open sets. Then what are the closed sets? Well, remember that a set is open if its complement is closed, or it's closed if its complement is open. So what I'll do is I'm just going to take the complement of every one of those. The complement of the empty set, of course, is X. The complement of X, of course, is the empty set. And then if I take the complement of the singleton 1, I'm going to get 2, 3, 4, 5, 6, 7. If I take the complement of 3, 1, 2, 4, 5, 6, 7. Take the complement of 1, 3. So 2, 4, 5, 6, 7. Take the complement of 6, 7. One, 2, 3, 4, 5. Take the complement of 3, 6, 7. So 1, 2, 4, 5. And then take the complement of 1, 3, 6, 7. And we would get 2, 4, and 5. All of these sets that are on the right-hand side of the equal to signs are all of the closed sets within this topological space. And remember that the closure of A is the intersection of every single closed set that contains A. So in other words, every set that's a superset of A and is closed. Well, let's see how many of those we have. Which of these closed sets, let me just put a little check mark next to them, which of these closed sets actually contain A, which was 2, 4, 6. So 2, 4, 6, so that would be this one. 2, 4, 6, that'd be this one. 2, 4, 6, this one. Nope, nope, and nope. So it's the intersection of those three sets. And what do they have in common? Let's see, 2, 4, 5, 6, 7, 2, 4, 5, 6, 7, 2, 4, 5, 6, 7. So it looks like the closure is 2, 4, 5, 6, and 7. Up here, when I went back to this interval, this half-open interval on the real line, when I closed it, I added 1 point to it. Here within this topology, when I closed the set 2, 4, 6, we actually added 2 points to it, the 5 and the 7. Is that intuitive? I mean, not really, but it at least allows me to work with the definition and kind of see what happens when I actually construct the closure of this set. Okay. So let's see how long. So we've got 12 minutes. So I'm going to go ahead and wrap this video up, and then in a subsequent video, I will prove a couple properties with the closure of a related to the closure of a set.